Let's talk about conservation of angular momentum. Recognize that there's basically three conservation laws that sort of permeate physics. There's conservation of energy, conservation of momentum, or linear momentum specifically, but what we've called conservation of linear momentum, and then conservation of angular momentum. That is the third one. And we could start from basically do the same derivation we did for conservation of momentum, except put in the angular analogs and get to the exact same idea that the total angular momentum before a collision is equal to the same after a collision. Or incident, because the classic example is the ice skater. Now, momentum itself, the linear momentum, or what we generally just say momentum, is mass times velocity. So angular momentum is the rotational analog, which is moment of inertia times angular velocity. So if we think about moment of inertia deals with how mass is distributed. The farther mass is distributed away from the axis of rotation, the greater the moment of inertia. So if you're a skater, think about that. You have an axis of rotation right there on the sort of as centered on your body as best as possible, and the basic structure of your body is going to be the same distance away, but your arms and legs are the part where they're different. So when the arms are spread way out, and just assume that they're spread way out, even though you can't see them all. When the arms are spread way out, you have, even though it's not much mass, it is farther away from the axis. And so we have, since r squared, it's mr squared, since r is squared, the distance is a much bigger impact than the mass. So the farther it is away, the greater the moment of inertia is. So when the skater pulls the arms in, the moment of inertia falls. And as the moment of inertia falls, the angular velocity will go up. And so that is the conservation of angular momentum. Another classic example are helicopters. That helicopter blades tend to spin around. Well, they do spin around, otherwise I don't think it's a helicopter. The helicopter blade spins around, so in order for the blade to spin, there has to be something pushing it. Well, if there's something pushing the blade to spin in a particular direction, there's got to be a reaction force pushing the rest of the helicopter in the opposite direction. And so you see it in movies sometimes when the rear propeller gets shot, that suddenly the helicopter starts spinning around, and that's because it should be spinning in the opposite direction that the blade is. So if the blade's spinning this way, the helicopter is going to spin in the opposite direction, and that's the same direction. And then it gets into a coordination issue of, can I actually demonstrate with my finger? So one's going this way, and the other one's going this way. So they'll be going in opposite directions. Hopefully you get the idea. So that's why you have the blade, is to try to basically push the helicopter, the main body of the helicopter, away from the way it naturally wants to spin. And so there are also other types of helicopters. There's one where there are two blades top and bottom, where the blades spin in opposite directions. And then there's, I think it's the Chinook, where you've got blades on two ends of the helicopter, two large blades on the end of the helicopter, both spinning to keep the whole thing from rotating. So that's conservation of angular momentum. And, I'm trying to stop it in the wrong place.